Physics Part 339. If there are n charged particles in a length of L of the conductor and each carrying a charge Q which pass a point in the conductor in time t, then the current in the conductor is given by I is equal to NQ over T. And the speed of the charged particle is given by V is equal to L over T. Hence, F is equal to B into NQ over T into L sine theta, and F is equal to B and Q V sine theta. The force is the force on n charged particles. Therefore, the force on a particle of charge Q moving at a speed V at an angle theta to a uniform magnetic field of flux density B is given by F is equal to BQV sine theta. The direction of the force will be given by Fleming's left-hand rule. However, it must be remembered that the second finger is used to indicate the direction of the conventional current. If the particles are positively charged, then the second finger is placed in the same direction as the velocity. Or if the particles are negatively charged, for example electrons, the finger must point in the opposite direction to the velocity. Consider a positively charged particle of mass m carrying charge q and moving with a velocity v as shown in the figure. The particle enters a uniform magnetic field of flux density B, which is normal to the direction of the motion of the particle. As the particle enters the field, it will experience a force normal to its direction. This force will not change the speed of the particle, but it will change its direction of motion. As the particle moves through the field, the force will remain constant since the speed has not changed, and it will always be normal to the direction of the motion. The particle will therefore move in an arc of a circle, as we can see in the figure. The force F is equal to BQV sine theta. In this case, sine theta is equal to 1. Provides the centripetal force for the circular motion. Hence, centripetal force is equal to mv square divided by r, which is equal to BQV. Rearranging the radius of the path is equal to r is equal to mv over bq. The importance of this equation that if the speed of the particle and the radius of its path are known, then specific charge, that is the ratio of the charge to mass, can be found. Then if the charge on the particle is known, its mass may be calculated. The technique is also used in nuclear research to try to identify some of the fundamental particles. The tracks of the charged particles are made visible in a bubble chamber. Analyzing these tracks gives information as to the sign of the charge on the particle and its specific charge. Specific charge of the electrons. We will now look at two important experiments, both involving forces on charges in the fields, which led to the information on fundamental properties of the electrons, its charge and its mass. The electron charge, the principle of a method to measure